Hi, everyone. I hope you're all having a great conference. Today, we're going to talk about safety and security in C++20. I do have a lot of material to get through, so if you'll hold your questions till the very end, we'll get to them then. If we run long, then I'll stay in the session afterwards to answer whatever questions you have. So before we begin with the material, I want to do a little bit of a primer on real-time embedded systems for the people that are in the room and listening to the talk that are not either real-time or embedded systems developers. It'll help make a lot of the comments I'll make later on make more sense. So the first thing we have to deal with in a real-time embedded sense is um, hard, firm, and soft real-time requirements. So hard real-time requirements are where any missed deadline will cause a total system failure. That'd be things like self-driving cars. Most aircraft today are fly-by-wire, so they're going to wind up having a lot of hard real-time requirements. I mean, if you in this case, this is really sort of the crashing planes and killing people moments where you blow hard real-time requirement and you've just simply the system itself has failed. So think about it in terms of you're driving down the road. A tenth of a second here or there may mean the difference between being in a crash and actually surviving the crash, or your airbags deploying. Um, a tenth of a second too late, you wind up having a serious injury instead of actually having a crash that's survivable. Communications, when we talk about hard real-time requirements, those are almost always done in hardware. You may do them with an FPGA or a custom design chip, but software is just too slow for them. So when we talk about hard real-time requirements, we're talking about requirements that absolutely positively have to be met. Firm requirements have a little bit of variability in them. We can miss the deadline by a little bit, and you can see the yellow line that as time goes on, the usefulness of that data actually winds up getting worse the farther away from that deadline you've missed. So that's things like audio and video, and UDP traffic tends to be that way. If you're drinking water out of a fire hose, then dropping a couple of packets here and there is really not going to be a problem. But you still have a real-time requirement for it. Soft requirements are actually more of what we see if you're doing things on a PC or a workstation, or you're doing it a large scale. The usefulness of it degrades over time, but we're not talking about having serious ramifications of missing it. So things like industrial mechanical systems and video games are examples of where we have a soft real-time requirement. Most of the people who have real-time requirements that we are concerned about, or that have or work in the embedded world, you're dealing mostly with hard real-time requirements or firm. So it is something that you definitely have to pay attention to, and something that you have to live with in the context of the work that you're doing. So there are a couple of different platforms. If you're talking about in the embedded world, there are bare metal boards where you have no operating system and you're running right on top of the hardware. So an FPGA would be an example of a bare metal board where you might have a soft processor with no operating system, which means you are now single threaded. So these are the ones where you have no operating system support and you're right on top of the board itself. Real-time operating systems are custom purpose-built designed operating systems that are designed specifically so that you can meet hard real-time requirements and still have some sort of functioning operating system. You have a scheduler. You've got one of the biggest differences between that and a traditional generic operating system is the fact that it's highly focused on determinism. So an example of an RTOS would be one that runs Pathfinder, which is on the surface of Mars, running around collecting samples. These are very small operating systems. They're very specific for that particular purpose. Embedded operating systems like Linux is a very popular one, are ones that are sort of the generic operating system that you're traditionally using, but it's stripped down to get rid of most of the stuff that an operating system will carry for usability and people playing games and things like that. And it's really designed there to have an operating system that gives you a full preemptive multitasking operating system, but without all of the overhead you typically would have. So I've done a lot of work on bare metal platforms. One of the things I've done in previous years was ground-based interferometry, where you have to take measurements very quickly, tens of thousands of measurements in a second. So you don't have the ability to carry the overhead of an operating system. Sometimes you might do that with an embedded operating system where you have a custom purpose-built chip that does nothing but carry the heavy load for the hard real-time requirements. while you use the operating system for more of a way of usability. I've also done work on the embedded operating systems where this would be things like a system doing police body-worn cameras or in-car video where you have a purpose-built chip that's actually processing the video, but you need another generalized operating system that has to live within a constrained environment to be able to handle and run the system. So the things that we really care about in terms of performance, memory allocations and deallocations. This is one of those places where you because these are generally unbounded in time, and because you're usually in contention with other processes on the system, we don't want to do memory allocations or deallocation. Now, as you go down that chart from where you have a lot of firm real-time requirements down to soft real-time requirements, you might relax that. But in general, if you're talking about anything that is safety critical, once the wheels have left the ground, or so in the case of an airplane, once you've started your takeoff roll, you're not doing allocations and deallocations. You have all the memory you're going to get. You've allocated everything ahead of time, because there is the possibility that you have memory starvation and a problem at a critical time, and you can't afford that. So in terms of safety critical systems, we don't want to do a lot of memory allocations and deallocations. You want to set it up before you go. Exceptions is another issue where on almost every embedded system I've ever worked, nobody uses exceptions. One, because they have memory allocations and deallocations. They're expensive. You have stack unwinding with them. If you throw an unhandled exception, it goes all the way to the top of the call stack and then puts the software into reset. So exceptions are generally, I've never seen anybody use them in safety critical, and I rarely have ever seen them be used in any sort of embedded context. Memory access is one of the things you have to be very careful of in an embedded world and a real-time world. Is you have to avoid any kind of paging of memory, because once you go to get that memory, you need it because you've got some sort of deadline and that you're trying to meet. And what you don't want to do is find out that that memory was actually paged out somewhere, and now you have to go back and find it. System calls, most of those tend to be blocking and unbounded in time, so you avoid those as much as possible. Priority inversions, we run into it because everything runs on a priority, which is very different in the way of a preemptive multitasking operating system. You have a lot of problems where you potentially have a low priority task that is actually holding onto a resource that a high priority task needs. So the high priority task is now blocked from operating. Pathfinder had this problem one time early in its life on Mars. They didn't find it here in testing, and they had it was a low priority task having to do with the weather, and they wound up blocking out a higher priority task, and a guard some sort of guard process was watching it, decided the system had a problem, and put the entire system into reset. And so it just kept doing that over and over again. Context switches, those are very expensive. You don't notice that if you're running it on a PC or workstation, but you will definitely notice any kind of context switches in an embedded system. Pipeline stalls, because time is precious and power is precious, you want to make sure that the CPU has always got work to do and it's not stalled out. Wait states, anything that causes you to wait is going to violate your timing restrictions. So what's in the box as far as C++20? So this is a release that's sort of on level with C++11, because there is an enormous amount here, and a lot of it, the top four on the left, is really sort of the game-changing features that we've put into the C++20 release, specifically concepts and ranges. Modules, if you're worried about your build systems, is a huge piece of too. And then coroutines is sort of a new way of doing synchronization between threads. A lot of the other things are more tactical in nature, but when you sum it all up, C++20 is really sort of the game-changing release that we had in C++11. And by the way, that C++20 is here. That's actually an actual video of the last time we met in person earlier this year. So go out and look at it. It's actually a pretty fun video. So what do I look for in new features? The first thing I look for is memory safety. Does it create memory safety issues? Does it eliminate it, hopefully? Sometimes we've created memory safety issues unintentionally. Does it rely on memory allocations and deallocations? 70% of all software vulnerabilities are based on memory access problems. So if you have memory safety issues in a feature, it's going to be something that you're not going to want to use in a safety critical or security context. Runtime determinism. Obviously, if you've got an embedded system and you've got hard real-time requirements, you have to have an operating system and you have to have features that are going to wind up being deterministic. That's It's one of the reasons why we don't use exceptions, is because they aren't deterministic, no matter how hard we tried with them. So does it help give you opportunities? Does it create problems with meeting your constraints? Is it a more deterministic solution than the one that I could program? Um, that is one of the, in fact, we'll talk about one later, and that becomes a big issue when you're evaluating something for a safety and security context. Concurrency, does it ensure atomic operations? Does it strengthen the concurrency model? Sometimes we put things in there that have actually not helped the concurrency model, and in this case, we have one new feature that actually, at least one new feature that actually does that. 100% uptime. As I said before, the last thing you want is to hit undefined behavior or find an exception is being thrown when the wheels are lifting off the ground of a modern day jet, because now all of a sudden you've got a system that may be in reset at a critical time, or when it's just seconds away from the main gear touching down. Code clarity and correctness. We often don't think about that, but does the new feature actually make it easier for us to understand the developer's intent? So many times we find bugs that are in code that is simply there because of a misunderstanding between the person who wrote the original code and the person who actually is trying to modify it later. Interfaces are especially vulnerable to that. Scott Myers did a really great talk about interfaces, and he coined the phrase making interfaces easier to use correctly and harder to use incorrectly. So you'll hear that a lot today. For code reuse, does it promote the use of well-known design patterns? Sometimes we can get into design patterns that are really not healthy for software, but does the new feature promote us and push us into the correct direction? Does it promote code reuse and generic algorithms? I know a lot of engineers will say that they don't like to use generic algorithms or generic programming. They won't do something as a template. But what you wind up finding is that you wind up doing you find a lot of copy and paste replication errors when you don't program from a generic standpoint. So these are the kinds of things I'm going to evaluate, that I use to evaluate a new feature, and what we'll talk about today. So let's start with on the syntactic sugar part. So aggregates got a lot of attention this time because aggregates are basically a collection of members with no constructors. But there were a number of inconsistencies in the standard that allowed you to actually do things like have declared constructors, but not actually provide them. So one of the things we've changed is from C++17, there was literally a 2-word change that goes from user provided explicit to no user declared or inherited constructors. So here's what that means. In this case, we have an account constructor that we've created for our aggregate, but we have deleted it. So we have declared it, but we have not provided it. So that allows line 12, where you can now go ahead and act as if that constructor, and you sort of bypass the constructor in order to be able to construct the object. So that was okay in C++17. That's now broken in C++20. So what that change did was eliminated a lot of the special rules for constructors that created a lot of inconsistencies. And one of the things that we are trying to do is sort of go and clean up some of these things where people can use sort of rules we never thought of and sort of bypass to do things that aren't really things that you were wanting to do. So this change eliminates a lot of the abuse that we were using with the aggregate. So in this case, what it really means in the end is, if it doesn't have a constructor, then it's an aggregate, and if it has constructors, it's not an aggregate at this point. So a lot of this was a consistency change, but we also got this part, which is a really nice add for this release, and that's designated initializers. So traditionally in C++17, you could initialize the values in there, but if you wanted to skip a value, you had no way of doing that. So in this case, you start from the top down when you're doing initialization. On the bottom one, what we have today, designated initializers, we stole this from C. This is sort of also known as C compatibility. So you have now the ability of going in and designating which initializers that you're going to initialize at the beginning, and then the rest get initialized to 0. So it's a nice add in terms of being able for code clarity. So of the 6 items that I mentioned before, this one, there is in C, you can do things out of order. In C++, because of the way memory is laid out, you have to do them in order. So the order will be enforced at compile time, which is nice for memory safety. You don't have any worries there as far as something that's going to cause problems by being out of order. It helps with code clarity and eliminates inconsistencies from the standards. So this was a nice win, not a huge one. It took a lot to get it in because it was a breaking change, and breaking changes always wind up having have us spend a lot more time trying to figure out what are the implications of actually breaking it. So where we get, if you haven't been using scoped enumerations, those have been in since C++11, and they're a fantastic safety capability within the language. One of the things that people, if you were to, on a normal enumeration up until C++17, if you were to try and go outside the enumeration range, it was undefined value. In C++17, that became undefined behavior, which that in itself is a security risk and a safety risk as far as using that. So this is a quote from Dan Sachs. It's actually in the proposal, and I have enormous respect for Dan. He was one of the people that I listened to a lot when I was first coming up in the embedded world. In fact, I found out last year, I got to meet him for the first time last year, and I found out that I had sent him an email 13 years before, and I had just casually mentioned it, and then he wound up going back and actually finding my email and forwarding it to me. It blew my mind that he actually still had that email. This is what we have added here is something that's actually fairly simple. In the case here, you have a normal use of a scoped enumeration, and you are having to put in all this cruft because you now have to, in order to fully define it, now you have you're doing this RGBA color channel over and over and over again, which creates a lot of cruft in the screen. So all we've done is just overloaded using, and so now you have the using enum with the RGB color channel, and now you have a much simpler, not only are you not having to write this over and over again or copying and pasting, but you don't have all that junk sort of sitting in there and all the cruft to get past. So this was a nice add. It's not earth-shattering, but if it helps people get people to using enumerations properly, this is a really good thing to add to the release. So this promotes the use of scoped enumerations. There's no doubt about it. I mean, nobody likes writing all that stuff over and over again, but getting rid of that hopefully will get people to begin using. If you are not using scoped enumerations, that really is the one you should be using rather than standard enumerations. This also helps with code clarity by removing crufts. So we had two sort of small, one to clean up some inconsistencies, and then one that we could now that helps accentuate a new feature. So everybody's favorite feature now is the TIE Fighter three-way comparison Spaceship Operator that's had all sorts of names. And everybody hears that and wonders what exactly were we doing in the standards committee. So the Spaceship Operator adds a new comparison library. It's more than just a single operator, but in this case, what it does is the Spaceship Operator automatically creates all of the comparison operators that you would need. In the ones that I have listed, these are the default semantic ones for in-order comparison. So this is sort of the default ones. This means that you really only have to write one line of code instead of writing all of those again. Again, copy and paste replication errors create problems, and now this eliminates a whole class of problems when it comes to operators. For the non-default semantics, you now have the capabilities that on the right of strong, weak, and partial ordering and equality. So this gives us a very powerful library for being able to write a lot of this code without having to write every single one of these operators. So on the left, you have how you would write this under C++17. And I was writing this piece up and then realized, oh, I made a mistake because I was copying and pasting everything. And then I found out that I'd made a little mistake, which was on line 14. It was very hard to find. But I left it in there because it is a copy and paste replication error because you're having to write these over and over again. On C++20, it's all down to one line now. So this is the standard in order comparison. So now you just simply have to write the operator equal sign, and it will create all of these for you, so that you don't have to worry about. Now you could have done that with CRTP, but CRTP adds a lot of boilerplate code, which also makes it possible to make mistakes. And now you have just one line to do it. The other nice thing that got added as far as this is concerned is that now you have you can actually use this as a direct comparison. So you can use that in an if statement. So if it's less than 0, that means foo1 is smaller than foo2. If it's greater than 0, then that's the reverse, and then it also can test for equality. And so this gives us an ability to have a very simple, this is a nice add that it gives you a very simple way of actually getting rid of a lot of code that we have a tendency to do copy and paste replication with. Then there is this, so Barry Reskin came up with this, where he wanted to be able to do comparisons of optional. So this piece of code, 19 lines, winds up replacing 30 different operators that he would have had to have written by hand. And that's where this library is going, is to be able to take away sort of the drudgery and be able to create a lot of this sort of out of the ether without having to do all of the writing yourself. So this is a nice add. I wasn't really a huge fan of it, but it's sort of grown on me as we've gone along. It doesn't have a lot of implications in terms of safety and security from the standpoint of how it operates in the code, except the fact that you're not going to create a lot of copy and paste replication bugs, that it now simplifies your interfaces. So instead of having all of these things listed out, now you've got a single line that allows you to just create these. And then it eliminates the need for more complicated solutions like CRTP, which may be a little more error prone. So this is also a nice add. And if you want to know more about this, Jonathan Mueller did using C++20's three-way comparison last year at CppCon. So go take a look at that, and he explains it more in detail. So let's look at the standard library. And I know we don't tend to use the standard library a lot in the embedded world, simply because it's not tuned for embedded applications. But I think this is for people who don't spend time in the embedded world. This is a really good. Some of these things that we have in here are really good for them to know how to fix safety and security. So this is, of all the things that we have put into C++20, this is the one I've got that I love the most, that I think actually is the biggest game changer that we have as far as safety and security for the embedded world specifically. So here we have a function, and we've got our function template, and we want to pass in some sort of a container, and we're going to sort it. So we put up our warning, which says, go ahead, you need to have a container that is sortable in it, which makes perfect sense given the name of the function. So in order to protect things, instead of trying to perhaps find out that there's going to be a runtime error because you didn't pass in something with sortable, we'll go and constrain it. So we want to constrain it using the requires. And we want to be able to sort of define what we mean by sortable. And that creates, and then we do a static assert. So we're catching this at compile time. So if you're passing something that is non-sortable in and trying to instantiate this template, then you now have the ability to catch this at compile time, which is what we want. We want compile time safety. We don't want to figure this out on the fly. So we're good. So the problem becomes is, what if we get the definition of is sortable wrong? What do you have to have? What attributes does a container have to have in order to be sortable? And if we get 3 out of 4 attributes, now we have, what we've done is we've turned an interface problem into a logic problem, because now the problem is going to be buried in the logic, and that is going to wind up being a runtime problem instead of an interface problem that we had before. So this is where concept comes in, and this is the one that I think is for me, from a safety and security standpoint, is the biggest feature we've put in. So we add the new concepts library, and it's been described as a type system for the type system, and it's based on the C++14 concepts TS. So you've had access to this for a while, but it's now actually in the language. And what this does is it helps you to describe the constraints in generic code that are required for that template instantiation. And what this does is it means now the interfaces can be made totally clear as to what the expectations are for using them. And the standard provides a ton of them. This is not even a full list of them, but you've got movable, copyable, you have move constructible, copy constructibles. You have a lot of these that have already been defined, which is really great for engineers because they don't have to go figure this out. Now, all of a sudden, they can just go start using these things, and like Lego bricks, they can create the correct interfaces to make sure that what you're passing in is actually what they need. So those attributes are defined right there in the interface. So let's look at how this would work. So here is the sortable concept that's defined right in the standard, so you can go and look at it. And this is This will tell you whether or not the container you're passing in is going to be sortable. So now the interface comes down to just simply, instead of type name or class, you've got it just simply says sortable. So now the interface is completely clear as to what they expect. Instead of having to go drag through the code and look and see, okay, what exactly are you going to be doing to it? Now all of a sudden the interface has the clarity we need. We also added the requires keyword. So the top one and the bottom one, they both resolve to the same thing. You can either put it in the template, its definition itself, or you can use the requires statement. Either one of these works, they all resolve to the same thing. I prefer the top one because now I'm looking at the interface as sort of at the top line interface, and I know exactly what is expected of it. But adding this requires keyword sort of created an interesting side effect that I'm not sure if anyone thought about or if it was just something that came out of it. But the code you're looking at is not deceptive. This does compile, and you do see two destructors there. And that's because now you have the requires keyword now allows you to go in, and whichever one of those destructors makes sense for when you instantiate that template, that's the one it's going to use. So your code can now have multiple destructors. And this was something that Jason Turner talked about a few weeks ago in his C++ Weekly podcast. So you now have the ability to have multiple destructors, which looks weird. You look at the code and you think, well, this isn't C++ code. This has got to be a different language. But in this case, you need to have a destructor to be able to handle where the object type that you're using is trivially destructible, and you need to have one where it is not trivially destructible. And this is how you would do it. It's very simple, very clean, and it makes a lot of sense. So there again, this is why I think concepts, even though it's got sort of this interesting side effect to it, is one of these great features we put in that will help safety and security. So this is a standard template library feature. All these things are built in. The standard template library has been changed a lot they've put this all throughout the standard template library. So you'll see this everywhere, plus you can make use of it. It makes the interfaces much more clear so you understand you can roll your own. One of the things that I am finding, though, is that the complexity of this for sort of the everyday developer may be a little more challenging. This is going to, I think, wind up being something that library designers use much more, where if you're the library designer on your team, you're going to be the person who's going to use a lot of this, and as you build your libraries, and then other people will simply enjoy the fact that they now fully understand at an interface level what the expectations are. So this is going to eliminate runtime errors and because it now relies on compile time checks, which is exactly what we want. It makes the interfaces easier to use correctly, harder to use incorrectly, just like Scott Myers has said so often. It promotes generic programming and a lot of code reuse. People, I think, in doing this, it makes a lot more sense to put things into libraries now instead of writing a single one-time use function. The only thing that I see in it is it's got a high level of complexity. This is going to be something, especially, and the type system is never easy to deal with in C++. This is going to be one of those things where we're going to have to sort of understand that it's going to add a lot of complexity that people are going to have to work through. And like so many things that we put in the standard, we're going to figure out as we go along sort of simpler ways to do these things and go back and refine it. As far as just large features that went in, ranges has got to be the largest feature and the one that's probably had the greatest impact in the code base, especially in the standard template libraries. So what ranges does is, we always had direct memory access where we were accessing things with indexes or pointers, and then we got iterators, and iterators were supposed to be so much more safe, and then we found out that iterators weren't as safe as we thought they were, and there were many times when we could do things with iterators that were actually pretty dangerous. Now, ranges actually sort of abstracts this away, and this is the principle of zero overhead abstractions, sort of in the living, where we've now abstracted this above what we had using the features and the functionalities we had before, but now you have a much more safe method of doing this because you're not having to write all of this boilerplate code and having to deal with iterators. You pass things off to the ranges library, and the ranges library handles it. And when we talk about, if you've never heard zero overhead abstractions, what we're talking about is not that there's no cost, it's that it is not going to create any more overhead than if you were to hand roll the code yourself. So ranges is one of those libraries, and it's been It's been in development for 5 or 6 years, and it has performed phenomenally well. So let's look at it the way we would normally do this. You have a vector, you pass it to a sorting function. You need to send the beginning and ending iterator so that you can iterate over the range and then do the sort. With ranges, all you do is just pass the vector in, and it takes care of finding the iterators and iterating over the range. So you don't have to worry about the iterators anymore. But there's a lot more that it's added. There are a lot of views that this library now adds. So here I have a map, and I've thrown in some elements, and then I'm going to go ahead and I just want to reverse the view. I'm not reversing the map. I just want to print them out in a reverse order. So now you have a reverse view, which takes some sort of a container and just prints them out in reverse. There is also, but one of the fundamental changes that's been made by Ranges library is going towards more of a functional composition style of programming. So in the last example at the bottom, I've got a series of numbers, which I'm going to mask. Line 3's got my masking logic, and then line 4 is going to take those masks, it's going to apply a filter based on the mask, and then it's going to reverse it, and then it's going to transform the data that's left and cube everything. So when I print this out, my list that was in the vector now gets printed out with just 3 numbers because the filters eliminated a bunch, plus it reversed them and did a transform. This is, when you're writing software, this is like writing really the simplest software you can write. It's very expressive, it's very easy to understand, so it's a huge win in terms of the ability to understand code. The problem is that pipe symbol is going to be deceptively expensive. All those filters and transforms that you're doing on there are going to be computationally expensive. So you're going to use that, and you're going to look at it and you think, wonderful, and then you're going to go back and look, why is my application running like it's the 1990s? And the reality is that if you get into the habit of using this without understanding the implications from a performance standpoint of what each of these is doing, you will wind up having code that looks wonderful but runs horribly slow. And that's probably the biggest reservation I have about ranges, is it allows people to write a lot of really inefficient code. So this is not a complete list. There's a huge number of these. So these are basically just range views. So if you've been listening to Sean Parent, there's nth element. You've got the ability to pull out the keys out of a key value pair. You've got the ability to pull the values out of a value pair. You've got the ability to transform or drop a certain number of elements. So there's all of this code has now been written and tested. It's part of the standard template libraries, which makes things much easier to do. Again, it's zero overhead from the perspective of you couldn't write this any more efficiently on your own, but it is not zero overhead from the perspective that pipe symbol is going to wind up being very expensive, and people might not appreciate that given the simplicity of the code they're looking at. We have a tendency to look at complexity of code or the number of lines of code we've written and sort of draw a conclusion about what the performance is going to be, where that pipe symbol is going to be hiding an awful lot of that, and so is really the ranges library. So from a safety and security standpoint, it's huge for safety because it eliminates most or all of the direct memory access or rationales for direct memory access or using iterators. There'll be times when you'll find you have it because there's nothing in the ranges library that does it. You could go and write something that follows the ranges paradigm and get the same thing. This is not going to be a range. Ranges library is not going to be something we use in real-time embedded. It's fine for traditional development, but it's not something for real-time embedded simply because does carry a lot of overhead. It is as thread safe as the underlying containers and algorithms, which means if they throw, it will throw. It doesn't change any of that. So it does have exceptions in there. So it's something that from an embedded standpoint, we probably are not going to spend a lot of time using. It does create really elegant functional style code, which is really nice to read and look at. It's wonderful. It's going to cause people to be, it's kind of like when we first got inheritance and polymorphism and we built all these 17,000 layers of inheritance, and then year in we found out that was just a horrible way to write software, and so nobody builds deep hierarchies and inheritance now. This will be one of those things where we're going to have to be very careful of where that pipe symbol comes in. So let's talk about concurrency for a minute. I asked this question, and every time I ask this question, half the room looks up and says, yeah, the T is thread safe. The other isn't really sure. Most of the time, what it comes down to is what everybody's thinking about is the control block. They're thinking, well, the control block, has to be thread safe. Therefore, the T is assumed to be safe too, and that actually turns out not to be true. So in this case, the T in a shared pointer is not thread safe, but the control block is. And I'm sure there's an explanation. I haven't gone and found out what it is, why we didn't make the T thread safe. And up until this point, up until C++20, we had some sort of sketchy ways of doing, making it atomic, and it looked kind of weird, and it uh, didn't really work out correctly. So now we've fixed that. So atomic shared pointer is now a template specialization of atomic, which means we have fixed we've now given the people the ability to be able to make that shared pointer fully atomic instead of just having the control block be atomic. Bear in mind, though, that shared pointer T is not thread safe in and of itself. The control block is, the T is not. Standard atomic just allows you to do that now. So this new specialization eliminates the need for manual locking like we're doing here. So this is an example that actually comes from the proposal. And here we have a class that's a concurrent stack. We're having to do lock guards. So lines 13, 20, 27, 31, or now you're having to do manual locking. If you forget, or if you mess up the lock and maybe you're shadowing the mutex accidentally, you have a much bigger problem and a much harder problem to go track down. So now on line 3, you just simply declare it as atomic. Now all of a sudden we get rid of all those manual locks. You've got some of the other code changes a bit, but it actually makes it much simpler code to look at. So as far as safety and security, because people do even in the embedded world use shared pointer, this is a huge safety win. So you do potentially have memory if you're using shared pointer incorrectly because you think it's atomic when it's not. This makes it easy to resolve a lot of memory safety issues. It eliminates the manual locking so that you don't have a lot of the cruft that's now in your code. It makes it much simpler. So it eliminates the noise. So I really like this one. This is a really nice win that we've put into the standard this year. So this is the coroutines it's the one that I understand the least, mainly because I've had the least experience with it, but it's also the one that I think is going to be the hardest for people to get their arms around. I went and asked another standard committee member what do they know about coroutines, and they sort of shrugged their shoulders and said, no, you need to go talk to this other person because it was very few people really understand it. And then looking the complexity of this, I think that's going to wind up being sort of the hardest part to get past with coroutines. So coroutines are a form of structured concurrency. What they do is it adds a new coroutines library, and it's a lot more than just what I'm going to describe today. There are some really good talks out there that will hopefully explain this. But I've noticed that even in those talks, the authors or the speakers in those talks can find it very hard to sort of explain this to sort of the general programming community at large. And it's not that they don't understand it; it's not an easy explanation. So this allows a function to yield its execution back to a caller. So they've added 3 new keywords, which is wait, yield, and return, plus a bunch of new types. So there's more to go through than I have time today. And I tried to think of, okay, what would be an example of some place where we might use coroutines in place of something that I've already written? So remember I said before is that one of the questions I have is does the feature make it easier for me to do something that I've done in the past? Is it more efficient? Does it create better determinism than what I could sort of roll on my own? So for embedded developers, we use a lot of state machines. So here you have a very simple state machine that just it's for a user interface, and you go through all the different states, and then it's just a sort of a typical state machine. And on the right, you've got how you might run a single-threaded. If you've got a single-threaded application like I've used a lot of times, each of the pieces that you need to deal with, they each get a call, they each get a little bit of time. So this is sort of your time slicing. So theoretically, the way coroutines would work is that you now have the while loop is now inside that user interface. You still have a state machine, but on lines 12, 17, and 24, what you're doing is you're yielding back to the caller. And this has a lot of implications. Normally, when you return out of a function, you're going to take something off the stack, and then you're going to go back to the caller, and then they'll get called again, which will add it back to the stack. So there's a lot of stack behavior going on with state machines. In this case, it's not doing that. And that I think is going to be part of the problem for the embedded world. So this yield will yield back to the calling function. So in this case, the main now looks a bit different, where you're using co-wait, which says it's going to call it and wait for it to return, and it will keep doing that and returning back to the function until it yields back. So you get really this sort of the same behavior out of it, and then you have a co-return at the end. And what you're generally returning is a future from this, although I don't have a lot of that written into here. This is a way of allowing it to yield back without having to constantly go into a function return, into a function return. So if you're not doing a wait, if you're not doing something that is a state machine, let's say you're trying to initialize a communications connection, you can at certain points where you're waiting for someone to respond, you can go ahead and yield back to the calling function, and then when it gets called back again, you pick up where you started. This was just the sort of the example I could come up with that sort of means more to embedded developers than anyone else. So the problem with coroutines, or at least I think where the complexity comes in, is you actually don't get coroutines. What you get is the tools to build your own coroutines, which I think is where all the complexity is going to wind up coming in. This is sort of a new way of thinking, and so trying to build these for just sort of the average ordinary developer in the industry, this is going to be a challenge to get past. Again, it doesn't rely on the stack, but it does use heap allocations, which is going to be problematic for the embedded world, depending on whether you're running on bare metal or you're running on something that's got an operating system. There is going to wind up being a significant learning curve, and I think almost with some of the other things we've talked about, this is going to wind up being library authors are going to be the ones that use this a lot, so that you're creating this rather than having individual developers sort of pick this up for a single purpose. You're going to really want the person to be who's the expert in coroutines to write libraries that help the developers on their team. The other thing is, and this is sort of more the question I have, is that we don't have and this happens a lot with things that we come out with in the standards, is we will come out with something and we really don't understand how it's going to be used, and we really don't understand all of the implications. And what we're looking for is feedback coming from the community. And so this is, I think, is going to be one of those ones where we have a real lack of industry experience with it. It's something that's brand new, a completely different way of thinking of things. And we don't really have any good performance metrics in real-term applications. We've got sort of what people have done in-house, but nothing that really comes back and says, this is how we can expect this to work in the general industry. So if you have anything like that, absolutely share it with the community, because I've not seen anything where we have this really deployed in a way that is sort of for the general development community. So it's going to use the heap. So as far as the 6 categories that we've been talking about for coroutines, it does use the heap to store state. That's going to be a problem for some embedded developers. It does allow you, at least the advertisement allows you to write safer concurrency, and I believe it completely. The people that I have listened to who've talked about this are absolute experts when it comes to concurrency, and I have absolutely no concerns whatsoever that it will not help you write safer concurrency. It will. I think the complexity is really the problem, which will make it a little more complicated for people to reason about code when they see this, and trying to figure out is what are the edge cases and what is sort of the implications of doing that. And then I think one of the things that I like about this is that if it gets people to tend to write more library code where you have these things built in and you're not having to write things from scratch each time, and so that helps promote code reuse, and I think it's a great thing. So I'm sort of reserving judgment. It's one of those things that I think you should sort of step into this sort of cautiously until we really understand how this operates, especially in a real-time embedded system. So we had some safety upgrades too. The printf family it's been around forever. It's horribly insecure. There's all sorts of mistakes you can make with it, mainly because they're mainly based around variable argument functions instead of something safer like variadic templates. They're all susceptible to things like information disclosure, and if you get the parameters wrong, things really can go haywire on you. And a lot of the functions that are in there are ones that we use to overflow buffers, which is, from a hacker standpoint, it's a wonderful opportunity. From ours, not quite so much. So the new format library basically takes the printf library and it reconstitutes it into a more modern approach. So these are going to be based on variadic templates, which are much more safer. So now you have guaranteed type safety. This is something we were never going to get with printf, since it's going back to the days of C. The one thing that, as far as an embedded world is concerned, the memory management is automatic, which means that you're think of standard string. You're going to be heap allocating things a lot. So from an embedded standpoint, we have to pay attention to the fact that it handles the memory management on its own. So but what it does is it basically takes us, for people who are non-embedded developers, it will take us from using a lot of C functions to a lot of safer modern C++ uh, functions. And one of the things that people hated about streams was that it made things a little more complicated to use, and it wasn't intuitive. But this new format library actually solves a lot of those problems. And again, this is another zero overhead abstraction product where we have it's been written in such a way that we couldn't roll any better than this. So it's going to perform sort of at the peak. Now, if you've got hard real time or even firm real time, and you have a determinism problem, this is not going to be the library for you. But let me show you what you get in the format. So they've given you a much simpler format. The options are a lot simpler. I don't know about the rest of you, but I usually have to keep a printf options list handy because I always forget them and I get them wrong in the wrong order and it doesn't work out. And so this is just a very simple way of creating a string that's got a very specific format. And that was always very hard to do with being able to using streams. So down the last example, there is a streams example where you're actually creating a string. It'll just say hello world. One of the things that you've even got an extra parameter, which it throws away and ignores, which is nice. And so now you have a way to format strings that is type safe. It's much safer because it's based on variadic templates, and you don't have to worry about some of the problems with printf. So this is a really nice win. It's not earth shattering, but if you use printf a lot, this is definitely something you want to move to. So even though it has all the safety, so there is sort of the side of it that says this is much more safe, this is much more secure, but the problem is that there's a lot going on under the hood that's not going to be workable for the embedded systems. Mainly the memory allocations and exceptions are going to be things we're not going to want to be able to, or not even at times be able to put into our code. So volatile, everybody's favorite keyword, the one that everybody doesn't understand, everybody seems to hate for reasons, usually people who don't even use it. So it's being deprecated and replaced by a new keyword token. Actually, that's a lie. It's not being replaced. We are deprecating a lot of sort of the bad behavior that people have used for it. So volatile, if you've never used it, is generally, and it's a little more complicated than this, but it's generally designed to tell the compiler not to optimize reads on a register because it could be changed outside of the view of the compiler. So the compiler has a tendency to look at things, and we'll see one here in a minute where it says, oh, there's no side effects to this, so I don't have to do this anymore. In this case, it is a CV qualifier, which you'll see it's actually in the standard and in the interfaces of a lot of the standard template library features, and it's all over the place. There's hundreds of places where it shows up. So there's no getting rid of volatile. You'd break huge amounts of code, so don't worry about that. But what we've gotten rid of is people would try and use it as a replacement for atomic, or they would try and do as a qualifier on return types or function parameters. And it just became one of those messes where people were really allowed to do a lot of things they shouldn't. And one of the things that we eliminated with it is what'll happen is if you're doing any of that, it'll wind up giving you a warning. That's partly a problem in that we tend to have a habit of ignoring a lot of warnings instead, because you will want to make sure that you either go through your warnings when you go to C++20 to make sure that you aren't doing this or somebody in your team isn't doing this, or turn your warnings into errors and catch them there. So it was sort of a simple change to the standard. It's from a safety and security standpoint, it is a huge win for the use of volatile, because volatile actually had a very narrow application, and we sort of have expanded it, and it really was not doing what people thought it was doing. So Jacob Ashton has did a talk last year at CppCon called Deprecating Volatile, where he goes through a lot of this, and it's a very good talk. So I would go and see that. So from safety and security outcomes from what we've talked about, and I didn't cover everything that was in the language simply because there is a huge amount that's sort of left on the floor. I tried to get the major things that I thought would be most interesting. So the biggest win for sure for me is concepts, but the complexity I think is going to maybe problematic. Coroutines, again, you have some questions about performance and complexity. Because you're not really getting coroutines. What you're getting is the ability to write coroutines. Standard format, if you're using printf in the embedded world, I think you're still stuck with printf simply because of the things that format does under the hood. But if you everywhere else, if you're using printf, switch to format. It is far safer for what you're doing. And atomic shared pointer now, remember the T is still not thread safe by itself. So we've just simply made it easier to be able to have an atomic shared pointer. Ranges, this will probably be the biggest win for traditional software development, not so much for embedded, if at all, but it is a huge win for memory safety because it takes a lot of that stuff, it abstracts it away to where now you're not having to touch raw memory as much without paying a huge price. Using enum, this promotes the use of scoped enumerations, and that's a great thing because if you're using standard traditional enumerations, you really should move on. The Spaceship Operator, the funny name, but it actually gives us a lot of behavior when you're talking, a lot of really good features when it comes to actually doing when you're doing comparisons. Deprecating a volatile, if you weren't abusing volatile before, this really won't mean much to you, but everybody else it will. And then aggregates, we eliminated a lot of the abuse cases and sort of the strangeness and the standard, and we got C-style designated initializers. So let's look at C++23 for a minute. We've got about 10 minutes left. Let's have a look at C++23. So some of the things that were coming are contracts that we're working on right now. So contracts were pulled from C++20 after they'd been voted in. It was sort of a late change, and a lot of it was just there was, I think, two different sides that had different views of what what contracts should be. So contracts, if you haven't heard of them, those are a way of specifying the pre and post conditions and any invariants that are in the function. These ensure that the function operates on the valid data. They actually exist before you hit the opening brace, and I'll show you that here in a minute. They help. The three big things, though, is that they help the compiler with optimizations. They give you a lot of capabilities for static analysis tools to know exactly what the pre and post conditions and invariants are. And then they're more expressive than error checking. A lot of times I see code where people's written a block of code, and if you see it written up somewhere, it'll say error checking removed in order for clarity. Well, a lot of code I see, you might as well have that label on there because there is no error, there is no checking of the data coming in, there's no validation of it. The problem with contracts, at least as they were and probably as they will be for as far as in the embedded world, is they throw exceptions or they terminate when they're violated, and that's going to be a problem for safety critical systems for sure. It's going to create problems for embedded systems because now you have the potential of an exception being thrown and you don't catch it. So this is what it would look like. You have an expects. We know the name. We expect the named length to be valid. We expect the queue not to be full. We want to ensure that it's not empty. So that's basically what they look like before we pulled them out of the standard. So from our standpoint, especially from an embedded standpoint, this is going to wind up impacting runtime determinism. I think you're still having to validate the data yourself and dealing with it gracefully because you don't want terminate or an exception being thrown. You won't have the access to exceptions to being thrown. So this is probably not something that helps embedded very well. Secure clear. This is a small feature change, but I think it's one that's very important because one of the problems you have when you're talking about side channel attacks is I've written something to memory. I may delete the pointer to it, but the memory is never scrubbed. So what we did is we go into a memset, so we'd scrub it, but we found out compilers were optimizing things in strange ways, because really what you want to do when you have a password or something, you want to get it, you want to use it, you want to clear it. You don't want to leave it hanging around in memory. So in this case, the problem is that we have gotten our password, we've used our password, and then we memset to clear it. But the compiler looks at that and says there's no side effects to this, so I can actually throw the memset away, which it does, and it does it very well. So secure clear would be a platform independent way of signaling to the compiler is you cannot get rid of this. You must do this even if there's no side effects, because again, it's kind of like volatile. The side effects are something that are outside of the purview of the compiler to be able to see. So this is a safeguard against memory side channel attacks and eliminate and if you've ever tried to do this where you're doing both Linux and Windows, they each do it differently, so it can be somewhat painful to try and have a single piece of code that actually handles either one of them. So this would wind up being a cross-platform way of doing it. Zero overhead deterministic exception. So the real reasons why we don't use exceptions are the minute you turn exceptions on, even if you don't use them, it bloats our code. So in the embedded world, we just don't deal with them. The other problem is that they're non-deterministic. If you throw an exception, you don't catch it, it bubbles at the top of the call stack, takes your application down. So these are nobody that I know of uses exceptions in the embedded world. It's too painful of a process. So what Herb Sutter is going for this is he's trying to take the expense out of them. So instead of what you would be throwing a traditional exception, you would be throwing an exception, but without all the overhead. So this is, and this comes right from his proposal. What you would really be doing is you would throw a statically typed, basically a static type by value, instead of throwing the exceptions that we traditionally have. You get something that's much simpler and it doesn't have all the overhead. So it's basically he's saying is it's exactly as efficient deterministic as a local return by value. Now, this is a proposal. It's not gone in. It's something that we're looking at right now. So it's not we're still still sort of being discussed and worked about. And you have a lot of people on both sides that either like this or don't like this. One of the things that, and you can see these are mostly red, I like that it eliminates the non-determinism because it does help with runtime determinism, but all the red is still there. You still have stack unwinding. You still have all of the problems with code clarity and correctness and code reuse that come, you've still got to have a try catch to make sure that you catch it. If you don't, it unwinds the stack. So he's basically trying to unify exceptions and return codes into one thing that we could all use. From his perspective, he sees it as that people who use return codes versus people who use exceptions are really practicing two totally different dialects of the language, which is totally true. I completely get that. The part I don't like about the exceptions is a lot of is one with the overhead, but two, I see a lot of exceptions being used for flow control, and that's not what exceptions were designed for. So we'll see where this goes in the committee. This is of all the things that we're working on in the committee, this is one of the things I'm most excited about that I think has the biggest safety security play for us. If you were to go look at the document or go look at the standard, you would find there's about 300 mentions of undefined something in there. And these are the little landmines that we step on. So the goals of this are to take the explicit undefined behavior that's in the core language and the implicit places where we find it and actually define it in a way that's human readable for us. Because if you've ever tried to read the standard itself, it's like reading a legal brief. And that's because it's mainly for standards library maintainers and compiler writers. It's not really for engineers who work on it every day. So here is sort of the explanation. We talked before is that if you are using an enumeration and you go outside the range, that it becomes undefined behavior. That's the relevant passage, but you can see it's not easy to find given all of the text and the legalese that's in it. So this is what you would get, exactly what I said at the top of this. So setting an enum to a value outside the range of enumeration of the enumerator is undefined behavior, and it points you back to where it is in the standard, and then it shows you an example of how doing this actually winds up causing problems. So why did I tell you all of this? So the reason why I wanted to talk about C++23 today is the fact that this is your opportunity to get involved. with the standards committee and with a lot of the working groups that are working on these exact issues. Now, typically you'd go to a standards committee meeting. Usually it's all around the world. It's expensive, but now given the state of the world, this is something you can do today and you can do without leaving your home. The same way you're listening to me, and none of us has left their home. The standards committees are all meeting virtually now, and that gives us an opportunity for us to go and for people who are not part of the standards committee to go and get involved. And these are some of the places you can. If you do not have to be a member of the standards committee to be involved in it. I am, only because I've been doing it for a while, and I wanted to make that commitment. But you can be involved in it without actually becoming a member. So SG14 is low latency safety and security, and I'll give you my contact information if you need help getting put in touch with the people who run these groups. I'm happy to do it. We have another committee, which is SG12, which is undefined behavior and language vulnerabilities. So these are actually in the C++ ISO committee. There is also another committee called WG23, which is language safety, and they do a lot. I'm on that committee as well. We do a lot where we are looking at the language vulnerabilities for C++ and how we can teach engineers to be able to avoid that. And undefined behavior is a huge part of that one too. Then, depending on what industry you're in, there's AutoZAR, which is a safety critical C++ standard for cars and airplanes. So it's for safety critical systems in general. Then there is MISRA, which everybody says MISRA is miserable. And part of that is simply because they're still currently stuck at C++ 98, and everybody has sort of moved on from that. So the last two are industry standards that you can still it'll be hard to participate, but you can still keep an eye on them. The top three are ones you absolutely can be involved in today, which will help you learn a lot more about safety and security when it comes to modern C++. So this is my contact information. My blog is at the top. My email address is in the middle. Down the bottom is my Slack channel. I'm on CPP Lang. Send me a Slack, send me an email. I'll be happy to put you into contact with people who run these groups so that you can get more involved. And again, as far as the standards committee, you don't have to be a standards committee member to get involved. And this is the time to do it now that everybody's working virtually. So we're actually a little over time, so I will stick around on the channel and answer questions if you have any. Otherwise, thanks for coming to the talk, and I hope you have a great rest of your day and a great rest of the conference.